They don't even realize we're in this water.
Too bad, we're gonna cause some pretty nasty health effects. Now look, it's our problem, right?
What you just saw was a visual representation of what could be the drinking water that you consume every day. For tens of years, drinking water has been found to contain microplastics, as well as heavy metals like lead and cadmium, and inorganic materials such as phosphates and nitrates. While in tiny amounts, in parts per million, the effects of these can be minuscule. However, with constant exposure, they can have adverse effects, including but not limited to cardiovascular disease, immunosuppression, and even reproductive health. Hi, allow me to introduce our project, the Water Analyst Pocket Pro. Our device aims to detect these pollutants at a microscopic level. Our device contains 3 main systems, each with its own unique method of detecting microplastics, heavy metals, and inorganic materials, respectively. Also, our device is small and compact, making it suitable and easy to use not only in lab environments, but also at your home as well.
One of the newest and greatest concerns in our generation is the prevalence of microplastics in just about everything. Microplastics have been linked to numerous adverse health effects. For quantifying such an elusive and damaging form of matter, we've come up with a pretty novel method.
Raman spectroscopy has a high-power laser to shine a light onto a sample. Most light scatters normally, but a small fraction scatters at shifted wavelengths. This is what we call the Raman shift, and every material has its own Raman signature that helps us to identify it. The method is non-destructive, has minimal preparation, and a high resolution. As a widely accepted method of measuring microplastics, and with bountiful research associated with it, the method has been decided as the best route of detection. Come on, let's go take a look at how this is set up.
This is a look at our setup here. First, we're going to start with the source. This is a 785 nanometer, 300 milliwatt laser. Just in front of it, you'll see our bandpass filter.
What the bandpass filter does is it cleans the wavelength of the laser to make sure it's purely 785 nanometer laser.
And then if we go here to these cylindrical lenses,
The beam comes out elliptical, like an oval shape. Because of that, the next 2 optics, cylindrical lenses, help to make it go back into a circle.
then moving on, this is our beam expander, otherwise called a telescope.
The next 2 lenses create what we call a telescope, or a beam expander, or in our case, a beam shrinker. It changes the beam from a super big circle down to a very small circle so that it can go inside the spectrometer. The super long distance is dictated for that very reason. Magnification is equal to the ratio of the focal lengths of the lenses. So we have a really small focal length, a 20 millimeter focal length lens, and a 500 millimeter focal length lens to make a beam 25 times smaller.
The next component is our Raman filter. This will ensure that the 785 nanometer laser wavelength is fully filtered out, leaving us with just our Raman signal data. And then the final part is our spectrometer, by which we will be taking all of our measurements.
While the diode is off, we can see we get no reading. But as we turn on the diode, we can see it goes through the plastic, the red dot there, and we get a Raman shift, around 3000 inverse centimeters. We can pause that and then copy it into clipboard where we can then record our data.
Microplastics isn't the only cause of threat that is contaminating our water supply. In current days, there's an increased rise in the level of lead and cadmium found in our water supply. And in order to make sure our drinking water isn't contaminated, we have developed a subsystem in our Berge Design project which detects heavy metals such as lead and cadmium and outputs the concentration that is present in the test sample. And we're going to be showing you that specific design right now.
Now we look at the setup that is used to actually detect the heavy metals present in the water. So this is just the basic setup, which includes the potentiostat and the screen printed electrodes dipped in the solution which we want to figure out the concentration and the heavy metals are. So for starters, what the potentiostat basically does, it sends out a small current throughout this circuit. That means it goes through the screen printed electrode, which consists of a working electrode and a reference electrode shown by these 2. As the current passes through the working electrodes and the reference electrodes, some of the metal ions present in the solution, such as the cadmium and lead, start being attracted to the negative charges in the electrodes and they start becoming deposited in there. The deposition of metal ions increases the conductivity of the circuit, and that causes an increase in current at specific voltages. Specific type of metal ions will cause a peak current at specific defined voltages. In case of lead, it's 0.5, and in case of cadmium, it's 0.1. So by looking at the graph of the current versus voltage, we can see the peak current and then the value at the voltage at which it occurs, and we can sort of determine what type of heavy metal it is. And by seeing how much current is flowing, you can determine the concentration. So basic general idea is the higher the current that's flowing, the larger the concentration of heavy metals because there's more metals being deposited.
Once the system starts up, the potentiostat creates its own wireless network, which we can connect via phone or laptop. And once connected, it takes us to a website, as you can see over here. So the web page is where the user interacts with the system, and the UI is very simple. It has a few modes, but we're going to mainly focus on the run CV. And once we run the CV, it takes the system about 4 minutes to complete the output. And once we get an output, we see that we can generate a graph of voltage against current, as well as the system shows the peak voltages, and by judging by the peak voltages, the system reads out the type of heavy metals that's in there, as well as their specific concentration. So it's very easy to use, and there's not much complication in it, and it easily tells the user how much metal is there and at specific ppm.
So now we're moving into our subsystem that detects phosphates and nitrates. Although those inorganics are found in various types of food, it is important to detect low limits and such as 0 to 100 ppm for those individuals who suffer from chronic illnesses such as kidney failure. So let's just get to it and I'll show you the system. So how this works is a commercial test strip is inserted manually in the cassette where a motor, which is a servo on a rack and pinion system, brings the cassette down into the enclosure where the ArduGam is integrated with our Raspberry Pi. After a certain amount of time, for the phosphate pad it is 3 minutes, and the nitrate pad it's 1 minute for processing. The Raspberry Pi takes an image where the sample is further decreased to that smaller square where a color analysis is performed. You can see that there is going to be an estimated parts per million for both nitrate and phosphate, but as color is very variable, we have changed it to be parts of bins. So everything that you have seen on the display isn't what the user is going to see. That is just for our verification procedures, which of course passed. What the user will see is just the concentration of nitrates and phosphates.
We needed a way to get the data from our sensors to the end user that was convenient and easy to understand. So creating a smartphone app solved both of these problems. This also allows us to lower the barrier to entry of analyzing water when compared to using specialized lab equipment.
With communication with our sponsor, our team has determined that the system has passed most of the verifications with customer satisfaction.